Okay, this will be 8-6. We're going to break it into two parts. It has two tests in it. This is the first one. It's called the ratio test. Just looking ahead, we should be testing Friday, November the 1st, I believe it is, on 8-1 through 8-6. So that leaves us with this section, then another day on 8-6, and then a day of review, and then a test. And that should be, let's make that November 2nd. Friday, November the 2nd. Just stop right here and pause the video and see if you can tell what each of these tests means. These are the 8 tests that we've done so far. Some of them are more like a process, like the integral test is more of a process. Some of them are a test where you just look at it and say, but see if you can, in your own words to yourself, describe these 8 things, just as a good self-check. Since we are nearing test time, you don't want to be catching up on all of these at the last minute. So go ahead and pause. And if you could tell what all of those 8 mean, at least for the most part, you're in pretty good shape. If not, flip back through the sections or make sure you ask in class, but don't let yourself get too far behind on this first half of Chapter 8 because the test is coming up soon. So let's get on to the first part of 8-6. Okay, this is going to be called the ratio test. And it's used, if you notice in your book, it says the ratio test is not a cure-all for all ills related to tests for convergence, but it is particularly useful for series that converge rapidly. Series that converge rapidly are going to be ones whose terms get to 0 very quickly, and the fact that they have factorials in them, that's one reason they would get there very, very quickly. So a hint when you would want to use the ratio test is if you see factorials, because the factorial is the most dominant on the hierarchy of domination. So if you have that in the bottom, your terms will be quickly approaching 0. And we'll see a couple of examples of how the ratio test works with factorials. So let me just give you the test first, and then I'll do one convergent and one divergent example. So we know that our series come in the form, the formula inside the sigma comes in the form of a sub n. What we're going to do in this test is take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And then check and see what that limit is. And when I say a sub n plus 1, that's just kind of a formula for the next term. For example, if a sub n is 2n plus 3, then a sub n plus 1 would be 2 times 2n plus 1 plus 3, or 4n plus, let's see, 4n plus 2 plus 3 would be 4n plus 5. So a sub n plus 1 is just kind of the quote-unquote next term based on calling a sub n the current term. So that's just kind of a generic terminology, but it just means that a sub n is your formula, and a sub n plus 1 is whatever your next term is. So you'll see this through the examples. 3 things are going to happen. Let's call this limit L for just a second. If L is less than 1, then your series, the sigma of a sub n, converges. And not only that, it converges absolutely. If you refer back to the last video on alternating series, converges absolutely means it doesn't matter if it's alternating or not, it just converges. If L is greater than 1, and your book says greater than 1 or infinity, that just means greater than 1 is different than infinity because infinity is not defined. So if it's a real number like 5, that's greater than 1, or if it's infinity, then your series diverges. To simplify things, I'm not going to put or infinity because I would assume that if you got infinity as your answer, you would say, hey, that's bigger than 1. If L equals 1, too bad. Don't know. Try another test. All right, so this is test for this limit. So basically, if you decide to use the ratio test, come up with a formula for the next term, put it over the formula for the current term, cancel what you can and find the limit, and then look for that limit to be less than or greater than 1 and make your conclusion. Okay, so let's get a couple of examples. First example is the sum from 1 to infinity of negative 1 to the n minus 1 times 3 halves to the n over n squared. And now, notice this didn't have a factorial in it. It doesn't have to have a factorial, but usually if it does, this is the one you're going to use. So what we need to do is come up with an expression for the n plus first term. A sub n is just this formula right here. And this thing, I'm going to go ahead and finish the ratio test, but I'm hoping that some of you are thinking, this thing, these terms don't even appear to be going to 0 because the top is exponential and the bottom is a power. And since exponential dominates power, we should see that these terms diverge to infinity. But just for the practice of using the test, I'm going to go with the ratio test. A sub n plus 1 is just this same thing, except all our n's are now n plus 1s. So here's my limit. And notice, I've left out the negative 1 to the n minus 1. This is an alternating series, but part of your limit is a big set of absolute values, which means all the terms are positive, so it doesn't matter if it's alternating or not. You just make them all positive. So those absolute values mean ignore the negatives. So my series, my limit is the a sub n plus 1 formula on top. And on the bottom is the current formula, just the regular formula that was given in the problem. So this looks like a crazy limit, but once we simplify a little bit, it won't be too bad. First of all, dividing by this fraction is the same as multiplying by that fraction flipped over. This is almost always going to happen in these problems. And you should see some stuff in common that you can get rid of. For instance, on the top, I have some 3 halves. I have 3 halves times 3 halves times 3 halves n plus 1 times. On the bottom, I have 3 halves times 3 halves times 3 halves n times. So, long story short, I've got 1 extra 3 halves on top. Whatever n is, there's an extra 3 halves on top. So this is completely gone, and that's gone, and there's just that 1 extra. Just think if n were 10, I've got 10 factors of 3 halves on the bottom and 11 on the top. 10 of them cancel, and that leaves 1 on top. All right, I also have an n squared on the top. And on the bottom, I've got quantity n plus 1 squared, which is n squared plus 2n plus 1. And really, you just need to know that it's 1n squared. The 2n plus 1 is insignificant because my ratio of coefficients is 3/2, which is the coefficients of the n squared. This is all that matters. And I have 3/2 over 1, which equals 3/2. So my limit equals 3/2. Now, if you remember the test, this is a value that's greater than 1. Therefore, my series diverges. Whoops, there's El Guapo. You know him from the Three Amigos. And so my conclusion here is my series diverges by the ratio test. And I don't want you to think that I'm going to make you do tests that aren't necessary. If I gave you this and just said, does this series converge or diverge, I would be absolutely thrilled if you said, this thing diverges because of the nth term test. The top dominates, so the terms don't go to 0, so therefore it diverges. But again, this was just for the sake of using the test. Let's try another example of the ratio test. All right, this example is the sum from 0 to infinity of, on the top we have an n factorial quantity squared, and on the bottom we have a 3n factorial. All right, so it's kind of hard to tell what do these terms do. If you plugged in a big N, you would see they are going to 0. The fact that the top is getting squared makes it really, really big, but the fact that the bottom is tripled before you factorial just even beefs up that factorial more, so it's really, really, really big. So the terms do go to 0, but you don't even, I mean, if the ratio test works out and it shows convergence, then we didn't have to really check to see that the terms went to 0, although you should always do that first. Anyway, the ratio is going to be, the limit is going to be the next term, which would be this same formula, except all my n's are replaced by n plus 1s. Divided by my current term. And what you'll want to do after you get used to this is go ahead and multiply by the current term flipped over. Because dividing by it and then flipping it over is just one extra line you didn't really have to do. Now, see what will go away here. This one's a little bit more complicated than they usually are, but we should be able to get some stuff to drop out and simplify a little bit. For example, this bottom is 3n plus 3 factorial. And the top is 3n factorial. And let's see, we've got an n plus 1 factorial squared on the top and a n factorial squared on the bottom. And if you think about what those are, let's just look at for a second n plus 1 factorial squared. So n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, 3, 2, 1. If I square that, then I'm just going to square every single one of those. So it's n plus 1 squared times n minus 1 squared, and so on, all the way down to 3 squared, 2 squared, 1 squared. N factorial squared is n times n minus 1 times n minus 2, all the way down to 3, 2, 1. If I square that, then I get n squared, n minus 1 squared. I square all those terms because they're not added together, they're multiplied. So if you go through and cancel everything, what you have left is n plus 1 quantity squared. So that's up here, and that's all gone on the other side. If you've got something like that and you're not sure what to cancel and what not to cancel, just write it out and take your time and see if you can figure out what they have in common that will cancel out. So what I have here now is some factorials that I can cancel. Think about this term here. It's 3n plus 3 times 3n plus 2 times 3n plus 1 times 3n minus 1. And when I get to 3n, that's where I pick up with the top and start canceling it out. So what's left is 3n plus 3 and 3n plus 2 and 3n plus 1. The rest of it's all going to go away because the 3n will cancel with the 3n on the top, and the 3n minus 1 will cancel with the 3n minus 1 from the top, and so on all the way down to 3, 2, 1. So if this is what's left, think about just your degree of the top. The top is n squared plus whatever. And that's not a difficult one because I could FOIL that and get n squared plus 2n plus 1. But my point is you don't really care about anything but the n squared. And on the bottom, if you were to multiply all of this together, FOIL the first two, and then take that result, multiply by the third term, you would end up with a leading term of n cubed. And it's going to be 3n cubed times 3n cubed times 3n cubed, which is 27 into the third, plus a bunch of other stuff. All right, I don't need you to multiply all that stuff out to know that the top is squared and the bottom is cubed. And the limit, if the top is squared and the bottom is cubed, is 0. And referring to 2 pages ago, if this limit is less than 1, it converges absolutely. So therefore, because I got 0, my conclusion is that n factorial squared over 3n quantity factorial converges. All right. So I know this has been a super long video, but it's really just half the section, and it's all on the ratio test. And of all the ones that apply to future things, this is the one that does so the most. So make sure you understand ratio test, because when we do some other things in the last half of Chapter 8, the ratio test is going to happen in those sections as well. So there's one example of each, and we'll do some more in class. I can't wait to see you then. Young out.